What if one planet shaped the fate of the entire solar system? What if it protected Earth from deadly comets, while hiding oceans that might harbor alien life? Jupiter isn't just big, it's powerful, mysterious, and full of surprises. From massive storms that can swallow Earth whole to moons that might glow in the dark. This is Jupiter, like you've never seen it before. Jupiter, the power and mystery of a giant Jupiter, a world of towering storms, lethal radiation, and breathtaking beauty. It's a cosmic giant so massive, it actually tugs on the sun itself. Jupiter has quickly become one of the most closely studied objects in our solar system, with 7 flybys, 2 orbiters, 1 still active, and 2 more missions on the way. There's still so much to uncover about the 5th planet from the Sun. What gives it that unmistakable reddish tint? What's it really made of beneath those swirling clouds? What secrets are hidden below that thick, mysterious atmosphere? And what have we learned about the legendary Great Red Spot? Jupiter plays a crucial role as a cosmic guardian of our solar system. And now, it's time to dive deep into its many mysteries. Jupiter, the 5th planet from the Sun, orbits just beyond the asteroid belt, nestled between Mars and Saturn. It lies about 778 million kilometers, or 5.2 astronomical units, from the Sun, and takes 12 Earth years to complete a single orbit. Jupiter's axis is tilted just 3 degrees, a minimal tilt by planetary standards. That tiny tilt means Jupiter doesn't really have seasons, unlike Earth or Mars, but similar to Saturn. Its equatorial radius is noticeably larger than its polar radius. This is a truly colossal planet, the biggest in our entire solar system. Its mass is so immense, it's about 1,000th that of the Sun. That might sound small, until you remember the Sun holds 99.86% of all mass in the solar system. Jupiter makes up nearly all of what's left. In fact, Jupiter's mass is 2.5 times greater than that of every other planet put together. Jupiter's mass and its gravitational dance with the Sun. And here's a fascinating fact. The center of gravity, Barry's center between Jupiter and the Sun, doesn't lie within the Sun, but actually floats above its surface, about 1.68 solar radii from its core. Let's take a moment to talk about barycenters. Normally, when we picture something orbiting something else, we don't imagine the smaller one pulling on the bigger one. And in most cases, like the ISS orbiting Earth or Mercury orbiting the Sun, that influence is tiny, almost negligible. But make no mistake, it still happens. A barycenter is the shared center of mass between 2 orbiting bodies, the invisible pivot they both spin around. Thanks to Jupiter's sheer mass and its distance from the Sun, its gravitational pull is anything but negligible. As Jupiter orbits the Sun, the two engage in a graceful cosmic dance, circling a point just beyond the Sun's surface. Let's break this down with a simple example. Imagine placing a heavy object on one end of a stick and a lighter one on the other. To balance the stick, you'd have to find the point where their masses equal out, the center of mass. Naturally, that balance point ends up being closer to the heavier side. Now picture that stick as gravity itself, with the Sun on one end and Jupiter on the other, and you've just visualized how a barycenter works. Jupiter's size, mass, and gravity. Even though Jupiter is the most massive planet in the solar system, it's far from the densest. Its enormous mass comes from its sheer size. If Neptune were blown up to Jupiter's size, it would actually outweigh it. Flip that around. If Jupiter shrank down to Earth's size, Earth would be over 4 times heavier. In reality, Jupiter's diameter is 11 times Earth's. and it's a staggering 318 times more massive. And as we all know, mass means gravity. That's why Jupiter's gravity is intense, more than double Earth's, clocking in at 2.528 grams at its cloud tops. Jupiter's gravitational pull is so powerful, it affects every planet in the solar system in some way. It's strong enough to rip asteroids apart and hold on to at least 67 moons. Some scientists even believe Jupiter wiped out countless objects in the early solar system and may have stopped other planets from forming entirely. One standout example, the asteroid Vesta. Some researchers think Jupiter's gravity is so far-reaching, it's slowly messing with Mercury's already odd orbit. So much so that in a few billion years, Mercury could either spiral into the Sun or get flung out of the solar system entirely. Jupiter, the solar system's cosmic shield. Right now, Jupiter might just be the unsung hero of the inner planets. If Jupiter weren't out there acting like a cosmic vacuum cleaner, those dangerous long-period comets wouldn't be getting swept up or getting nudged just enough by its gravity to get flung completely out of the solar system. Jupiter is the fifth planet from the Sun, about 5 times farther out than Earth, and yet it still shines as the third brightest object in our night sky, right after the Moon and Venus. To show just how bright it is, grab a simple handheld camera and you can spot Jupiter without breaking a sweat. With a peak brightness of -2.94 magnitude, Jupiter can literally cast shadows. Its brilliance makes it a perfect target for backyard astronomers. And thanks to modern telescopes, you can now spot stunning details right from your backyard. Jupiter's clouds, color bands, and the Great Red Spot. So what creates those iconic swirling patterns we see? Jupiter's cloud layer is surprisingly thin, just about 50 kilometers, and it's made up of ammonia crystals, similar to Saturn's. But those vivid colors, they come from compounds rising up from deep inside Jupiter after being heated. These substances, called chromophores, interact with ultraviolet light from the sun once they reach the upper clouds, producing those breathtaking multicolored bands. It's a dynamic cycle, and Jupiter's appearance can shift dramatically over time. While the colors may change, the bands themselves stay locked at certain latitudes, consistent enough that scientists have given them names. However, their widths can expand or contract over time. The borders where these bands collide are stormy and turbulent. That's where the power behind the legendary Great Red Spot comes from. This is no ordinary storm. It's so massive that Earth could fit comfortably inside it. It's been around for as long as we've been watching, first spotted back in the 1600s. It may even be a permanent fixture on Jupiter's face. Interestingly though, it's been shrinking since we started tracking it. We still don't know exactly why it's red, and its color can shift wildly from deep brick to nearly white. The leading theory: UV light from the sun breaks down chemical compounds in the storm just like it does across the rest of Jupiter. The storm sits much higher than the surrounding clouds, giving it more exposure to sunlight and possibly intensifying its color. That might explain why its hue is often more intense than anything else on the planet. But Jupiter's storm game doesn't stop with just one fascinating cyclone. Take Red Spot Jr., for instance, a storm born from the fusion of 3 others between 1998 and 2000, which has managed to steer clear of its larger sibling and has become a striking feature in its own right. If it doesn't share the fate of another storm that got swallowed by the Great Red Spot, it could survive for centuries. What's inside Jupiter? A planet of hydrogen and pressure. So what exactly makes up this gas giant? Well, just like Saturn, Jupiter's interior transitions from gas to liquid, and eventually to metallic hydrogen. The deeper you go, the more intense the pressure gets. At extreme pressure, hydrogen starts behaving like a metal. Beneath all that lies what's likely an icy or rocky core. Since we can't replicate Jupiter's insane pressures here on Earth, we're still unsure how those core materials actually behave. Jupiter is believed to be about 90% hydrogen, 10% helium, with tiny traces of methane, ammonia, and other elements mixed in. Jupiter spins at breakneck speed, faster than any other planet, completing a full rotation in just 10 hours. But because it's not solid, it doesn't spin evenly. The poles lag behind the equator by about 5 minutes. When I was a kid, I always wondered, why isn't Jupiter a star? I mean, it's massive, right? And it's made mostly of flammable hydrogen. So shouldn't we just toss in a match and light it up? Well, unfortunately for my childhood self, stars don't quite work like that. And besides, there's barely any oxygen on Jupiter, so fire wouldn't stand a chance. Stars get their energy from nuclear fusion, driven by the crushing pressure at their cores. According to scientists, Jupiter would need to be about 75 times more massive to ignite like a star. Interestingly though, its volume isn't that different from the tiniest red dwarfs we've discovered. Jupiter's rings and magnetosphere, the planet of invisible power. And yes, if you look closely, Jupiter really does have rings. They're nowhere near as flashy as Saturn's, but Jupiter has 4 faint planetary rings. The main ring is razor thin, but surprisingly bright. The others spread wider, but they're extremely faint and hard to detect. The main ring stretches about 6,000 kilometers across, with one notable feature, the Métis Notch. Another standout feature of Jupiter, its incredibly strong magnetosphere, 14 times more powerful than Earth's. That's all thanks to the liquid metallic hydrogen swirling deep inside. It's the strongest planetary magnetic field in our solar system, second only to the Sun. Why does this matter? Well, there are a couple of really compelling reasons. First, magnetospheres funnel solar wind into the poles, creating stunning auroras. Second, Jupiter's 4 biggest moons are shielded from solar wind, since they orbit safely within this massive magnetic bubble. That means they don't need strong magnetospheres of their own. Jupiter's got them covered. But don't get too comfortable. This doesn't mean they're safe from radiation. Jupiter has an intense radiation belt, strong enough to wreck any spacecraft that dares to pass through. The closest of the big moons, Io, cuts right through the heart of this hazardous radiation zone and gets blasted with 3,600 rem of radiation every single day. To put that in perspective, exposure to that dose would kill a human in under 4 hours. So yeah, not exactly a vacation spot. Io, the volcanic engine of Jupiter. I'll just touch briefly on Jupiter's major moons here, since I've already covered them in a separate video. Jupiter boasts 67 known natural satellites, most of them tiny. 51 are less than 10 kilometers wide. But its largest ones, the Galilean moons, rank among the biggest in the entire solar system. Io, Europa, Ganymede, and Callisto, each one has a unique story to tell. Ganymede, in fact, holds the title of largest moon in the solar system. Its diameter even beats Mercury's. And with that in mind, take a look at Jupiter in infrared. It really shows the planet's vast scale and power. That little dot near the bottom? It's the scar from a cosmic impact, one that, had it hit Earth, might have ended life as we know it. We're lucky Jupiter's out there, not just for its beauty, but for the protection and insight it gives our entire solar system. Io orbits incredibly close to Jupiter. just 350,000 kilometers above its cloud tops. From the surface of Io, Jupiter would dominate the sky, appearing 39 times larger than our moon does from Earth. It completes a full orbit around Jupiter in just 42.5 hours, lightning fast compared to our moon's month-long cycle. During parts of its orbit, Io's surface can bulge by as much as 100 meters due to extreme tidal forces. It's a similar effect to ocean tides on Earth caused by our moon. Except on Io, it's cranked up to a whole different level. On Earth, tides typically shift about 2 meters between high and low, nowhere near Io's dramatic upheavals. Io experiences over 3 times more tidal force than our moon does on Earth. Thanks to its closeness to Jupiter and the gravitational tug-of-war with neighboring moons, Io's orbit stays locked in a slightly eccentric shape. In other words, Io isn't getting a break from this gravitational stress anytime soon. A day on Io equals its orbital period. Just like Earth's moon, Io always keeps the same face turned toward Jupiter. Io is a fairly large moon, even though it's the second smallest of Jupiter's Galilean satellites. It's about the same size as our moon and has a similar density, so its surface gravity isn't all that different. But here's a surprise. Io actually has the highest density of any moon in the solar system, just one of its many standout traits. It's also mostly made of silicate rock and iron, just like Earth, the other rocky planets, and our moon. That's a big contrast to most large moons out there, which are usually a mix of water ice and rock. In fact, Io is the driest place we know of in the entire solar system. Its core is probably made of iron or iron sulfide, wrapped in a silicate-rich mantle and crust. But unlike Earth, its core likely isn't convecting. There's no sign of a magnetic field around Io. The upper mantle, though, is believed to be partly molten, at least 50 kilometers thick, and that's where all of Io's volcanic power comes from. That's where all the volcanism comes from, and it leads us to the most mind-blowing thing about Io. Its surface is littered with hundreds of massive, active volcanoes. Back before the 1970s, Io was a mystery. We knew almost nothing about it. But telescopes had started to reveal clues. It seemed bone dry and possibly coated in sulfur. Pioneer 11 was the first spacecraft to give us any real look at Io. The images weren't sharp, but they confirmed one thing. Io wasn't icy like other moons. It was rocky. It also had a thin, barely there atmosphere. Pioneer 10 was supposed to snap close-ups too. But Jupiter's brutal radiation fried its command system. The spacecraft was hit with radiation 10,000 times stronger than anything near Earth. Then came Voyager 1 and 2 in 1979, missions that changed everything. Voyager 1 zipped by just 20,000 kilometers away and captured stunning close-ups of Io's surface. What it revealed was jaw-dropping. Vibrant colors everywhere, and not a single impact crater in sight. Voyager spotted mountains taller than Everest and volcanic pits stretching hundreds of kilometers across. And yes, it saw what looked like rivers of lava carving across the terrain. But the real shocker, massive plumes erupting straight from the surface. It confirmed Io as volcanically active, the only place beyond Earth where we've directly seen this, excluding ice volcanoes. This was the smoking gun. Io is volcanically active, and to this day, it's the only place beyond Earth where we've seen real lava eruptions, not counting cryovolcanoes. Voyager 1 also confirmed that Io's surface is blanketed in various types of sulfur frost. That sulfur is what paints Io in those wild alien colors. Voyager also found that sulfur compounds dominate Io's thin atmosphere. Voyager 2 got a look as well in July 1979, though it was cruising a distant 1 million kilometers away. Even from that distance, it managed to spot 7 of the 9 volcanic plumes Voyager 1 saw earlier, which meant those eruptions had continued for months. But the truly game-changing images came from Galileo, which arrived at Jupiter in 1995. Galileo wasn't built specifically for Io, yet it still captured some of the most detailed images we've ever gotten of the moon. Unfortunately, Galileo didn't operate at full capacity. Mechanical issues held it back from reaching its full potential. And that means we missed out on what could have been even sharper, more detailed views. Still, Galileo managed to catch plumes erupting from multiple volcanoes and confirmed that those volcanoes were spewing sulfur and silicate-rich magma, just like volcanic flows here on Earth. Though on Io, the magma is especially rich in magnesium. Io's surface is a riot of color. The yellow plains come mostly from elemental sulfur, while the bright white patches are fresh sulfur dioxide frost. Near the poles, radiation alters the sulfur, turning those regions redder than the rest of the moon. Elsewhere, red patches are fallout from volcanic plumes that soared hundreds of kilometers into space. One of the most dramatic deposits came from a volcano named Pele. Pele was quiet during Galileo's visit, but Voyager 1 had previously caught it mid-eruption with a spectacular plume. That plume towered 300 kilometers high and stretched 1,200 kilometers wide, basically the size of Alaska. Interestingly, on Earth, lava usually pours out of the crater at the top of a volcano, those classic summit depressions. But that's not the case on Io. Those summit craters are missing from its towering peaks. Instead, Io has enormous lava lakes rimmed by tall walls of rock. Take Loki, for example, the biggest volcanic depression on Io, stretching 200 kilometers across. These lakes are linked straight to underground magma reservoirs, though a thin crust often forms across their surfaces. Loki alone pumps out about 25% of all the heat released by Io's surface. But when that crust collapses and sinks, Loki can suddenly blaze with 10 times its usual heat. Europa, the ocean beneath the ice. Europa is easily one of the most fascinating moons in the entire solar system. It's a stunning, icy world cloaked in mystery. Here's the very first close-up of Europa, captured by the Pioneer spacecraft way back in 1973. Since then, Voyager and Galileo have both flown by, and with each mission, Europa continued to surprise us. Let's start by looking at where Europa fits into Jupiter's moon system. Europa is the second closest and smallest of Jupiter's 4 Galilean moons, yet it's still the 6th largest moon in the whole solar system. It's only slightly smaller than Earth's moon, measuring roughly 3,000 kilometers across. Europa completes one orbit around Jupiter every 3.5 days. What's fascinating is that Io, Europa, and Ganymede are locked in a 4:2:1 orbital resonance. Their mutual gravitational pull keeps their orbits slightly stretched, never perfectly circular. As Europa moves closer and farther from Jupiter, it's constantly squeezed and stretched by tidal forces. And those forces matter. They shape Europa's surface and stir what lies beneath. Europa's surface is largely composed of water ice, cold, bright, and pristine. And what makes it instantly recognizable are the long, continuous fractures crisscrossing its icy shell. These features are known as lineae, Latin for lines. Each lineae may be just 1 to 2 kilometers wide, but they can stretch for thousands of kilometers across the surface. We're still unsure exactly how or why these enormous cracks form. But the leading theory suggests tidal flexing pulls the crust apart, allowing warmer material from below to rise and fill in the cracks. A process similar to how ocean ridges form on Earth's seafloor. In this Galileo image, you'll spot some curious dark brown patches dotting the ice. They're relatively small, about 10 kilometers wide, and they're called lenticula. Scientists believe lenticula are formed when warmer, less dense material rises beneath the surface, sometimes pushing the crust upward, or, in other cases, bursting straight through it. When that subsurface material does break through, it creates bizarre landscapes known as chaos terrain. These areas are rough, jumbled regions surrounded by otherwise smooth, icy plains. Scientists think these zones might be softer and could hold vital clues about what lies beneath the ice. Galileo data suggests Europa's equator might be lined with sharp, icy formations known as penitentes. These jagged ice spikes could rise as high as 15 meters, likely carved by intense direct sunlight at the equator. Interestingly, penitentes exist on Earth as well, in high, dry regions, but they're much smaller than the giants possibly found on Europa. Even though Europa is as old as the solar system itself, its surface has surprisingly few craters. Europa has fewer than 50 major craters. Compare that to the Moon's 5,000-plus craters over 25 kilometers wide. This tells us Europa's surface is constantly being reshaped and renewed. Estimates suggest Europa's icy crust is just 30 to 180 million years old, a geological baby. It also holds the title for the smoothest known solid surface in the entire solar system. Europa's icy crust reflects a lot of sunlight. It has an albedo of 0.64, among the highest of all moons. That brightness makes Europa about 5 times more reflective than Earth's moon. But Europa pays a price. Its surface gets blasted by intense radiation from Jupiter. The daily radiation dose at Europa's surface is a staggering 5,400 millisieverts. At that rate, a human would be fatally irradiated in just 1 day. The reddish-brown stains on Europa's cracks likely come from salt and sulfur mixed with ice, and altered by Jupiter's relentless radiation. A recent study by NASA's Jet Propulsion Laboratory suggests Europa may actually glow in the dark. High-energy radiation from Jupiter penetrates Europa's icy surface, exciting molecules just beneath it, causing them to release faint visible light, like a cosmic nightlight. Sadly, we can't observe this glow from Earth because Europa's dark side never faces us. It's always turned away behind the sun. We'll need to wait for future space missions to confirm whether Europa really glows in the dark. Jupiter's radiation also plays a big role in shaping Europa's ultra-thin atmosphere. Europa's atmosphere is incredibly thin and mostly made of oxygen. But unlike Earth, Europa's oxygen comes from a process called radiolysis, meaning radiation hits the icy surface, splitting water molecules into hydrogen and oxygen. The lightweight hydrogen drifts off into space, while the heavier oxygen tends to stick around. The escaping hydrogen and oxygen help create a neutral gas cloud that trails along Europa's orbit around Jupiter. In 2012, the Hubble Space Telescope spotted massive water vapor plumes erupting from Europa's south pole. The plumes soared as high as 200 kilometers above the surface, an astonishing height. Then, in 2018, astronomers uncovered even more evidence of these watery eruptions. By reanalyzing Galileo's old data using modern processing techniques, future missions that study these plumes could tell us what's inside Europa without needing to land. Because what's hidden beneath Europa's icy shell might just be its most intriguing secret. Beneath the crust, scientists believe a global ocean lies sandwiched between the ice and Europa's rocky mantle. The first clues to this hidden ocean came from Voyager in 1979 and later from Galileo in the 1990s. Those missions recorded a dramatic shift in Europa's magnetic field over time, which only makes sense if something beneath the ice, like a salty liquid ocean, is conducting electricity. Europa's outer shell shows more signs pointing to a liquid layer hidden below. It rotates with a slight tilt of 80 degrees, which wouldn't happen if the crust were locked to the mantle below. Instead, it's likely that Europa's icy crust floats freely on a liquid ocean. In fact, the crust may slowly drift, completing a full rotation every 12,000 years. This floating crust could explain the web of cracks, those lineae we see all over the surface. If tidal forces were the only factor, those cracks would be localized, not spread across the whole moon. But since the crust slowly shifts over time, any one spot doesn't stay still, so new lineae keep forming as the surface moves. Europa is freezing cold, with average temperatures hovering around minus 160 degrees Celsius. Yet thanks to tidal heating and maybe some radioactive decay, liquid water still exists beneath its icy shell. Scientists estimate the ice crust is about 15 to 25 kilometers thick. Below that, the subsurface ocean might plunge as deep as 60 to 150 kilometers. That would give Europa more water than all of Earth's oceans combined, by more than double. Europa checks all three boxes for life: liquid water, essential chemicals, and an energy source. That's why it's one of our top contenders in the search for extraterrestrial life. To dive deeper into Europa's secrets, 2 missions are now in the works and set to launch soon. First up is NASA's Europa Clipper, slated for launch in 2024. The second is ESA's Jupiter Icy Moons Explorer, JUICE, scheduled for launch in 2023. Clipper will perform dozens of flybys using a powerful instrument suite to assess Europa's potential to host life. JUICE will mainly focus on Ganymede, but it'll also make at least 2 flybys of Europa. Ganymede, the magnetic moon. Now let's shift our focus to the largest moon in the entire solar system, Ganymede. Ganymede is the 3rd Galilean moon and the 7th moon out from Jupiter. With a radius of 2,634 kilometers, it's the only moon in the solar system that's actually bigger than Mercury. That's right, not just similar in size, but physically larger than Mercury, though its mass is only about half of Mercury's because Ganymede has more ice and less dense rock. Even so, it has more volume than Earth's moon and Pluto combined. To put it in perspective, Ganymede is roughly 40% the size of Earth. If Ganymede orbited the Sun instead of Jupiter, we'd likely call it a planet. It takes Ganymede 7.15 days to circle around Jupiter once. Just like Europa and Io, Ganymede is tidally locked, always showing the same face to Jupiter. Ganymede probably has a metallic iron-nickel core wrapped in a rocky silicate mantle. Above that lies a massive shell of water ice covering the moon. Thanks to internal heat, scientists believe a good portion of that ice layer is actually liquid water. Beneath its crust, there could be a subsurface ocean over 100 kilometers deep. That hidden ocean might hold more water than all of Earth's oceans combined. Despite Ganymede's frigid temperatures, tidal heating and radioactive decay likely keep that ocean from freezing. But perhaps the most intriguing feature, Ganymede is the only moon known to have its own magnetic field. Galileo detected this magnetic field back in the 1990s. Scientists think it's generated by a molten iron core spinning inside, just like the Earth's magnetic field. Ganymede's magnetic bubble exists inside Jupiter's much larger field, and the two constantly interact. Ganymede's surface is a fascinating mix of two distinct types of terrain. Some areas are dark and ancient, heavily pocked with impact craters. Others are lighter and younger, marked by long, parallel grooves cutting across the ice. Scientists think the lighter zones were shaped by icy tectonics, where Ganymede's crust cracked and spread apart. That movement created ridges and troughs, similar to how plate tectonics work on Earth. Meanwhile, the darker regions may be leftovers from Ganymede's original ancient crust. Even the younger regions aren't pristine. They're still littered with impact craters. All of this suggests Ganymede stayed geologically active for a surprisingly long time. Cryovolcanism, ice volcanoes, might have helped reshape parts of Ganymede's surface. The European Space Agency is now building the JUICE mission to study Ganymede up close. JUICE will enter orbit around Ganymede in 2034, becoming the first spacecraft ever to orbit a moon beyond Earth's. Callisto, ancient and undisturbed. Callisto is the fourth and last of the Galilean moons, and Jupiter's second-largest satellite. It's the farthest of the four, orbiting Jupiter at almost double the distance of Ganymede. Callisto is a peculiar world, its surface scarred by countless ancient craters. In fact, it holds the title of the most cratered object in the entire solar system. Unlike its Galilean siblings, Callisto appears geologically dead, quiet for billions of years. There's no evidence of tectonic shifts or any recent resurfacing activity. Its crust has stayed nearly the same for over 4 billion years, a true relic of the early solar system. Oddly enough, Callisto's surface is surprisingly flat. Even though it's packed with craters, they don't rise into tall peaks like those on the moon. That might be because Callisto's icy surface slowly flows over time, gently evening out the land while keeping the crater outlines intact. Underneath its frozen crust, scientists believe Callisto may harbor a subsurface ocean. That ocean could lie 100 to 150 kilometers beneath the icy surface. Even if it doesn't touch a rocky seafloor like Europa's, it's still considered a possible habitat for life. Unlike Europa, Callisto isn't blasted by intense radiation. That makes Callisto one of the safest spots in Jupiter's system for a future base or outpost. A lander, or even a human habitat, wouldn't face high radiation or ground-shaking activity here. Jupiter's hidden halo and captive moons. Jupiter has rings as well, though they look nothing like Saturn's majestic bands. They're so dim, we didn't even know they existed until Voyager 1 flew by in 1979. The rings are mostly fine dust, likely formed by micrometeoroids striking Jupiter's tiny inner moons. Jupiter's ring system has 3 main parts: a thin main ring, a puffier halo inside it, and 2 faint gossamer rings beyond. The halo is broad and thick, but almost invisible, even in close-up images. The gossamer rings likely come from dust ejected by Amalthea and Thebe. Unlike Saturn's icy rings, Jupiter's are made of tiny dark grains of dust. Beyond the Galilean moons and those near the rings, Jupiter hosts dozens of small, irregular satellites. Most of them are likely captured asteroids or pieces of shattered moons snagged by Jupiter's powerful gravity. Unlike Jupiter's main moons, these irregular satellites follow wild, tilted, and stretched out orbits. Many of them even move in the opposite direction of Jupiter's spin, what astronomers call retrograde orbits. Most are tiny, just a few kilometers wide. The biggest, Himalaya, is only about 170 kilometers across. All told, Jupiter has 95 confirmed moons, and we're still discovering more. Jupiter's legacy, a guardian, a mystery, a wonder. Jupiter's sheer mass has helped sculpt the very structure of our solar system. It serves as a cosmic shield, pulling in or deflecting dangerous asteroids and comets that might have otherwise hit Earth. But it's a double-edged sword. It may have also flung some objects inward, triggering major impacts on early Earth. Some theories even suggest Jupiter helped bring water to Earth, or possibly prevented even more from arriving. Its influence is enormous, deeply complex, and still not fully understood. We're still digging into its secrets, trying to learn how it formed and what exactly lurks at its core. We don't even know for certain whether Jupiter has a solid core. The Great Red Spot is mysteriously shrinking, and no one knows why. Its moons, especially Europa and Ganymede, might harbor life in the oceans beneath their frozen shells. Jupiter is a planet of extremes, a planet of puzzles, a source of wonder. It's more than a swirling giant of gas and storms. It's an entire system of worlds orbiting one colossal planet. It's a protector, a destroyer, a beautiful enigma. It is, and always will be, Jupiter. Thanks for watching. If Jupiter fascinated you as much as it did us, don't forget to like, subscribe, and share the wonder, because the journey through our solar system is just beginning. And next, we'll take you beyond, to the icy edges, burning giants, and perhaps other Earths. Join us for the next cosmic chapter.